Hey everyone, welcome back to Chem Story. Today, we're diving into an important concept in organic chemistry, ring strain. Have you ever noticed that some rings in organic chemistry are incredibly stable while others are super reactive? Why is cyclohexane so special compared to other cyclic compounds? Well, the answer lies in ring strain. So today, we're going to break down what ring strain is, what causes it, and how we can actually measure it. By the end of this lesson, you'll understand what ring strain really means, what it's made of, and how we calculate its energy. Let's get started. Ring strain is a key concept in organic chemistry, and understanding it helps explain why some cyclic compounds are more stable than others. When the two end carbons of a straight-chain alkane are joined together to form a ring, that change introduces strain, because the molecules' bond angles and internal interactions get distorted. This strain mainly comes from three sources: angle strain, torsional strain, and steric strain. To deal with that, cycloalkanes naturally adopt specific three-dimensional shapes that help minimize strain. But not all rings can escape it. Cyclopropane, for example, stays highly strained because of its rigid triangular structure. Angle strain happens when the bond angles in a ring don't match the ideal 109.5 degrees we expect from sp3 hybridized carbons. In smaller rings, like cyclopropane and cyclobutane, the bond angles are way smaller than they should be, and that creates a lot of strain. Basically, the smaller the ring, the more angle strain it has. Now compare that to cyclohexane. It can twist into a chair conformation, which completely gets rid of angle strain. That flexibility is what makes cyclohexane much more stable than those smaller, more rigid rings. Torsional strain comes from eclipsing interactions between neighboring bonds, just like what we see in acyclic alkanes. In cyclopropane, all the CH bonds are stuck in an eclipsed conformation, which makes the molecule superreactive and unstable. But in cyclohexane, the chair conformation lets the bonds stay staggered, which means torsional strain is minimized. And that's a big part of why cyclohexane is so stable overall. Steric strain happens when atoms or substituents get pushed too close together, and that leads to repulsive interactions between them. In plain, unsubstituted cycloalkanes, steric strain is usually not a big deal. But once you add bulky groups, it can become a lot more noticeable. One classic example of steric strain is the 1,3 diaxial interaction in cyclohexane. When a bulky group ends up in an axial position, it bumps into hydrogen atoms that are in the same plane, and that creates extra strain. That's why the equatorial position is almost always more favorable for large substituents. This effect becomes especially important when we look at substituted cyclohexane compounds, which we'll dive into more in our next lesson on cyclohexane conformations. We can actually calculate the energy from ring strain by looking at the heat of combustion of a cycloalkane molecule. The heat of combustion tells us how much energy is released when the compound reacts with oxygen and burns completely. By comparing that value to a strain-free reference compound, we can figure out how much extra energy is coming from ring strain. To calculate strain energy, we measure the heat of combustion for the cycloalkane we're interested in, and compare it to the heat of combustion of a reference compound, something that doesn't have any ring strain, like cyclohexane or a straight-chain alkane. The difference between those two values tells us how much strain is actually present in the ring. If a cycloalkane gives off more energy per Ch2 unit than a strain-free compound, that's a clear sign there's ring strain in the molecule. Since the heat of combustion naturally goes up as the number of carbon atoms increases, we don't just compare the total energy. Instead, we look at the energy released per Ch2 unit. That gives us a fair comparison across different ring sizes. For cycloalkanes, the general formula is CnH2n, so using this idea, we can normalize the combustion values. That way, we can clearly see how much extra energy is trapped in smaller, strained rings, compared to larger rings that are much more stable. To figure out how much ring strain a molecule has, we compare it to reference compounds that don't have any strain. We usually use acyclic alkanes or cyclohexane for this, since both have a heat of combustion per Ch2 unit of 157.4 kilocalories per mole or 659 kilojoules per mole. Cyclohexane works especially well as a baseline because it's basically free of ring strain, so it gives us a clean comparison. If a cyclic compound has a higher heat of combustion per Ch2 unit, that tells us there's extra energy stored in the molecule, which means it's under strain from unfavorable distortions in its structure. When we look at a table of ring strain values, we can see how different ring sizes stack up in terms of strain energy. Cyclopropane and cyclobutane have the highest strain energy per Ch2 unit. They're under a lot of angle and torsional strain. Cyclopentane has less strain, but it still deals with some torsional strain because of eclipsing interactions. Cyclohexane, though, is in a league of its own. It has virtually no strain, which makes it the most stable cycloalkane. When you go up to larger rings, like cycloheptane and cyclooctane, strain starts to creep back in, not because of bond angles, but because of ring flexibility and awkward conformations. A graph of ring strain energy really helps make these trends clear. Cyclopropane and cyclobutane show up at the very top of the graph. They've got the highest strain. Cyclopentane drops a bit lower, showing a moderate decrease in strain. Then we hit cyclohexane, and it's right at the bottom, zero ring strain, thanks to its perfectly relaxed chair conformation. But once we move beyond six-membered rings, strain starts creeping back in again. Not as extreme as the small rings, but still noticeable because of all the twisting and flexing in those larger structures. So to sum it up, ring strain comes from three main sources: angle strain, torsional strain, and steric strain. We can measure it using heat of combustion, and the data clearly shows that six-membered rings are the most stable, because they can adopt conformations that are basically strain-free. Now that we've covered the key concepts, it's time to put them into practice. Next time you come across a cyclic structure, take a second to think about what kind of strain might be affecting it. Thanks for watching, and I'll see you in the next video.